Welcome, Computer Organisation. Today we're looking at different ways in which data can be represented. We've looked at binary numbers. What we want to have a look at now is other number systems. And then we'll also look about how characters, text, and colour can be represented on a computer. So, computers work in binary. We work in decimal. But when you just work in binary numbers, there's lots and ones and zeros, and it becomes very cumbersome for us humans to deal with. So we tend to use two different number systems. There's octal, which is base 8, and that obviously uses the digits from 0 to 7. And then when you get to 8, you write it down as 1, 0. And so it uses the same place number system concept. So you've got 8 to the power 0, which is 1. The next column is 8 to the power 1, which is 8. The next column is 8 to the power 2, which is 64, and so on. That one we use, but probably not as much as we use hexadecimal. Hexadecimal is base 16. So base 16, we choose 16 because that's 2 to the power 4. That means a single digit in base 16 represents 4 bits. And that means you need 2 digits to represent a single byte in base 16. And that is really quite useful. The problem is, if it's base 16, we need 16 digits. We've got 0 to 9, that's the first 10, they're sorted. The next 6 will become the first 6 letters of the alphabet. Typically, we use capital letters as well. So A represents 10, B represents 11, C 12, and so on, all the way up to F, which represents 15. Then obviously when you get to 16, that gets written down as 1, 0, 17, 1, 1, and so on. We'll look at the number 6, ACD 16. This can be converted to decimal as follows. We write out our 4 columns, that's 16 to the power 0, 16 to the power 1, 16 to the power 2, and 16 to the power 3. Those in decimal represent 1, 16, 256, and 4096. I've now got, in the least significant bit, I've got a D. That means I need, D represents 13. It means A, B, C, D, 10, 11, 12, 13. So 13 comes down in our first column. Our second column is C, that represents a 12. And that column is worth 16. So we do 16 times 12, and that's 192. Then our third column, we have an A. A is 10. Our third column is worth 256, so we've got 256 times 10, that's 2,560. Our third column is worth 4,096, and there's a 6 in that column, so we need 6 multiplied by 4,096. That is worth 24,576. So to now work that all out, I need to add those 4 numbers up. 24,576 plus 2,560 plus 192 plus 13. And that gives me 27,341. So hopefully you see, if you got comfortable with how to work with binary, we're using the same concepts here for hexadecimal. It gets just a little bit trickier because now it's not just ones and zeros. You can go all the way up to F, which is worth 15. So we need to take that value of that column, say 16 squared, that's worth 256, the third column. And we multiply by the value that we've got to get the full value. And then you add it up. So there's a few steps there. Again, make sure you understand how to do that. Next, I'm going to talk a little bit about text. Again, we just hold text as numbers, or the computer holds the number. A number represents a text. So what we have some sort of lookup table. If I've got this number it means the letter A. If I've got this number, it means, I don't know, the multiplication sign. If I've got this number, it means an exclamation mark. Now, there are two standards that became very popular. Early on, there was the ASCII standard. There were a few competing ones, but ASCII probably became the most popular because that was the one that was used on personal computers. And so for that we have like a lookup table, and we have the value, decimal value 65, that represents a capital A. The decimal value 110, that represents a little n. And you just look up the value on the ASCII table. That's what we get. The problem with ASCII, it used 7 bits, almost a byte, and it was great for most Western European countries. The United States, the UK, France, Germany, maybe they started to have some problems because they use accents in their characters, acutes, umlauts and so on, and those were not counted for. But ASCII only used 7 bits, so what they did was the last bit, they had as an extension to ASCII. That's where we could now have these extra characters, these accents on characters, and we could also use it maybe for some more mathematical symbols and for geometric shapes that maybe we wanted. So that became quite good, but it wasn't good enough for when we went to maybe Asian countries. If you look at Japan, they have 3 character systems: hiragana, katakana, kanji, the Chinese characters. And so there was no way this was going to be held on ASCII. So they started to come up with their own standards, and they came up with different ones, and these standards were unable to talk to each other. So what we needed was one standard to unify them all, and that standard became Unicode. It was there to support all the languages. It can support millions of different characters. So you've got Arabic, you've got Chinese, you've got any character system that you can think of is supported by Unicode, or can be supported by Unicode. There's a number of different encoding systems that come within Unicode standard. UTF-8 is probably one of the most common ones that we use these days, and it is backwardly compatible with ASCII. That means if I have a, 110, that means an N both in ASCII and in UTF-8 Unicode. So that's how text is held. And again, at the base of it, it's just numbers. And we know those numbers are binary numbers. Okay, the next thing I want to have a look at is colour. So first we need to think about, well, how does colour work? And we're working with light here. So we need to think of how light creates colour. So in light we basically have 3 primary colours. We have red, green and blue. If you had 3 LEDs of that colour and we focus that onto a single point, and we had a red LED, a green LED and a blue LED, and we flicked them around, sometimes we put one on, put the other one on, maybe we took 2 on, we would find that we'd get a red light if we just have a red light on. If we put red and green on, we're going to get a yellow. If we get red and blue, we get what is known as magenta. If we put all 3 on, we now get white light. If we turn them all off, we get black. And that's the idea of how we can start to use colour on a computer. The other thing that we can do is we can work with different intensities of light. So instead of turning the red light on full, maybe only put it on half. And then when I put the green light on, instead of getting a nice bright yellow, I'm getting a darker yellow, a brown. And so that's, as I said, that's how a computer will hold colour. We've got different ways in which we can change the intensity. So we use numbers for red. Instead of just having red on and off, we can say, let's put a whole byte there. It doesn't have to be. There are different systems around. We could have a whole byte for red, a whole byte for green, a whole byte for blue. And then we can say, well, I can now give a number, because I know a byte goes from 0 to 255. I can give a numerical value for my red, a numerical value for my green, and a numerical value for the blue. And that is how we end up getting millions of different colours. Computers can also represent other data. You're listening to me now. That sound, that is just behind the scenes, that is numbers, saying whether we have a peak here or a trough, and that gets converted onto your speaker as sound coming through. So everything that we hold in a computer, every single piece of data that you can think of, behind the scenes, it is binary numbers.